Hi, Ani. Are we ready to start the surgery?
Yes, so our patient here is prepped and we're ready for robotic surgery.
Okay, let's get you connected to a surgeon.
Sounds good.
All right.
Hey guys, how are you? It's Dr. Yunus up in New York. Can you hear me okay?
Yep.
Yes.
Great. Well, here we are, guys. We're back at our roots in New York City. Got Ben here, CEO of Monogram.
Hello and welcome. Thank you everybody for joining our second live stream. We're going to up the ante today. I think you're all going to be very, very excited. As Dr. Yunus said, we're back where it all started. This is where the magic began. So our office actually used to be up the street a couple blocks in the heart of Brooklyn. We started, Dr. Yunus founded the company in 2016. So that'll give you some idea of how old we're getting.
Yeah. So we're up here on the 18th floor of this building. I'll give you a quick tour of New York City before we get going. Manny, if you want to see out the window here, we got the Statue of Liberty out there. Ellis Island's right across from that. You got the Staten Island Ferry just pulling in, and Wall Street, Freedom Tower. That's Brooklyn Heights down there. You got up here, we're looking up the East River. Here we've got you got the Brooklyn Bridge right out this window, and the Manhattan Bridge. You can kind of see there's the Empire State Building way up in Midtown there. So that's our perch right here in the middle of New York City, and we're going to do surgery down in Austin, Texas, almost 2,000 miles away in a few minutes.
And for any investors having an aneurysm about how much this view costs, don't worry. We didn't have to pay for it. This is courtesy of Doug's office.
So what we're doing today is, we're going to do remote surgery. So I'm going to be controlling the robot with this foot pedal here, and Ani down in Austin has done the surgical exposure. And I'm going to be talking to him about the kind of the surgery part of it. So he's my eyes, ears, and hands in Austin, but I'm going to be controlling the robot remotely. And this is the same foot pedal that we will use in the operating room. And the idea here is, and Ben can chime in, is the idea here is not to say that we're a remote surgery company and we think we should be doing remote surgery tomorrow. But we really want to just show the robustness of our platform and just show the capabilities of what it can do, and really show the safety of what our platform can do, that the surgeon can safely make cuts from 2,000 miles away because of kind of what's inherently built into our system.
Sure. And I'm going to talk this up a little bit more than you did. So we think this is going to be the first time any surgical robotics company has done a remote surgery live. We are about 2,000 miles away from our Austin headquarters where the team is, and we'll introduce them in a second. But what I think is going to blow people away is just how the latency of our system is incredibly low. It's responsive, it's intuitive, even for a surgeon that is 2,000 miles away. We've designed our system to be for the surgeon to stand exactly where they would for a manual knee replacement, but what we really want to show is our technology is pushing the envelope in terms of safety, robustness. Just it's future compatible. So we're envisioning where the market's going to go. We have a phrase we say at Monogram: we're trying to skate where the puck is going. We're not trying to look at where the puck is right now. So I think we're in a pretty exciting spot, and we're going to show the team today what we've been working on for the past 12 months, and it's pretty impressive. Cameron, why don't you kind of show off the team in Austin, introduce some of the folks who have been working tirelessly on this.
I'd like to introduce the best team we have in surgical robotics.
Hey, Cameron,
Did we lose somebody?
did we lose you guys?
It seems so. Yeah. They just need a second to fix my microphone.
Okay.
We're
Okay.
good? Yeah, I'd like
While
to
these two
introduce.
While they're
I'd
getting
like to
set up,
introduce the best team to you.
while you're getting set up, Cameron, why don't we look a little bit at the latency that Ben was talking about? I'm gonna go live with the robot here.
So before you even start, let's just really explain what the system works. So, the system is a fully surgeon in the loop type system. So the surgeon is driving the robot at all times, and they're really in control of everything the robot does at all times. That control is input via a foot pedal. It's just like a gas pedal on your car. So Manny, why don't we show the foot pedal here?
Yep. So here it is. It's you can. I'm gonna go on live, so I'm not moving.
So yeah.
So forward, like an accelerator, from kind of 0 to 100 and everything in between. Back, if you want to go backwards, you can have a side swipe to kind of have other functionality like clicking points, etc. We have our emergency stop button, some other buttons for different functionality. But it's very, as Ben was saying, it's very much set up almost like a car pedal. So it'll be very intuitive to most users. And then the rest of the surgery can be controlled through the laptop, so this is our surgical plan. We're going to go through that later, but a lot of the surgical planning can be done beforehand. Tweaks can be made during the surgery depending on the situation. Anything else, Ben? I was going to show the jogging.
Yeah, I think you nailed it. So to kind of just show folks how responsive it is, what we're going to try and do here is show Doug moving the foot pedal and just give everyone a sense of the latency. So let's make sure we go to 3 views so that we can see the robot and the foot pedal.
Yep.
So
here,
Manny, let's get the foot pedal.
Manny,
on the live stream, we need to go to 3 views.
Okay. So I've got it set to live on the robot. So I'm going to start moving it. That's me. That's in real time. I mean, it's like, from what I can see, it's basically like I'm standing in front of the robot. I mean, it's real time here. It's honestly, it's amazing. I did not think it was going to be this good. It's literally the same as if we were in the room.
We're not showing the right view. Let's make sure we get the right view. So let's put on the big screen, guys. We want to see Austin on the big screen, and we want to see Doug's foot pedal on the smaller ones, just so everybody has a sense of what's happening here.
Yep. Okay, ready to go?
Yes.
Okay, so I'm going to move the robot again. And again, I mean, to me, it's like I'm attached and hardwired to the robot. And now I'm going to go to what's called home. Let's see how that goes. So I'm going to click home, and this will bring the robot to what we call the home kind of safe position. Beautiful.
Yeah, so everybody can see it's basically nearly almost instantaneous response time, and we're again 2,000 miles away. Doug is fully in control of the robotic system.
Yeah.
Sure. Yes.
So, is Cameron, your mic is all fixed? Okay, you want to introduce everybody down in Austin?
Yeah, let's meet the team.
By the way, South by Southwest is going on right now, so Austin is mobbed. Austin's probably got more people in it than New York right now.
Yeah. So like you said, we are all in Austin. We are in our cadaver lab at Monogram. Here we have our staff clinical engineer, Ani, who would be like Doug, you mentioned, it would be your hands and eyes here. And help you together perform the surgery. We have the director of implants, Chris Seifert, with us here. We have senior manager of hardware, Gerardo. Senior manager of platform software, Pedro. And we have the director of software, Mohammed. We have the manager of systems, Daniel, with us too. And in the background, we have other team leads. It's great to have you all here. So this team and all the other people in their teams help put this system together. Here we have the embossed system. It is connected to a simple wall connection, internet connection. And on the New York side, Doug's platform or computer is connected to this system to a simple hotspot. We're not using any fancy internet. We're not using any kind of fiber optics. It's just simple internet that you have at home. So some of you might be familiar with the morphology of our system. We have the robot cart sitting back there, and the arm extends all the way, and it's pretty much out of the way. We have the tracking setup over there, and the tracker tracks all these different components and the leg and femur and tibia of the patient. And then we also have the station through which Doug can plan a procedure, and with the help of Ani, together can perform the surgery.
Okay.
Sure. So just one quick comment here. So some of the benefits of the system, and this is based on how many labs are we at now, Cameron? Yeah. So we bring in surgeons to evaluate the system, and what we want is a collaborative robot. We want the surgeon where they would be if they were doing a manual knee replacement, for example. We don't want the system. We don't want surgeons accommodating the needs of the robot. So the robot is always coming into the knee on the medial side. The tracking camera is on the same side as the robot cart. The surgeon basically has the whole lateral side of the patient unobstructed. We've really minimized the occlusion problems. So it's really a low risk that somebody's going to walk in front of the tracking camera and occlude the arrays. The surgeon has easy line of sight to the navigation screen, but also the surgery itself. So it's unlikely the surgeon's ever going to have to turn their back on the patient to look at a screen or check something out. The arrays are pointed away from where the surgeries happen, so we mitigate the risk of splatter and contamination of things that need to be tracked. The proximity of the arrays to each other and to the rigid array that helps us figure out where the robot is, that proximity helps minimize error of the system. So all of these things it's taken a huge amount of effort to come up with this configuration. And I know it might seem obvious now that it's working, but it really wasn't obvious from the onset. And we think we're the only robotic system that has this morphology. And we think it's going to be really valuable in the operating room. Our goal is to have a robotic system that is collaborative and unobstructive.
Yep. And part of the reason we can do this is we've designed the robot. Like if you look at the cart, we've designed it so that the robot kind of comes off at an angle so that it can be placed on the far side of the patient. It doesn't need to be right up next to the operative side. The robot, the arm itself has a really long reach and a lot of 7 degrees of freedom. So it's able to be a little bit further away from the patient, enabling us to put it kind of on the far side of the operative extremity.
Exactly.
It really does help. I mean, as a surgeon, having that stuff out of the way, you've got a clear view of what you want to see. And it not only does it just improve the ergonomics of the surgery, but it's just safer. Because you've got a really good look at all the critical soft tissues that you need to keep an eye on during the surgery to make sure everything stays safe.
Yeah, and also, Doug is not going to be holding retractors during the surgery, but our system allows the user to have both hands basically to do surgery. So we would, recommend that a surgeon holds retractors, or their focus should be on doing surgery, and they should have both hands free to do it. So
yeah, that's one of the reasons we elected to go with a foot pedal configuration, is because we specifically wanted to keep the surgeon's hands free to do what really is critical, which is keep the patient safe.
Sure.
All right.
So okay. So right now we're in the surgical plan, and this is maybe we can show the guidance application now. I think we should probably transition to 3 screens just so we give the users all the information they need. So let's just make sure that the the live stream gets up there so that the audience can see.
Yeah, are we good on the planning
Okay,
screen?
yeah, there we are. So
Good.
we're on the planning screen.
Okay, so from here, I can make all the tweaks and do like an initial plan, and that's kind of how I would normally do a robotic surgery. Is, I'll just kind of based on the way I do a knee. I do something called kinematic or anatomic alignment, where I'm really trying to restore their anatomy to pre-arthritis. But there are different ways. You can have a classic mechanical axis technique where everybody gets a limb that's aligned, straight a certain way. There's a trend toward doing this more personalized alignment. And there's good data showing that patients do better when you give them back their anatomy rather than somebody else's. But that's kind of beside the point here. The point here is to show that the surgeon can remotely, if needed, or before the surgery even start, before the day of surgery, you can tweak the initial plan. And then we will, so I can, let's say, for example, I'm on the femur here.
So,
I want to change.
Cameron, it's, I believe, 1/2 degree increments on rotation and 1/2 millimeter.
So
Does
I'll
that
go
sound
ahead
right?
so these are my resection levels. So you see 8.2, 8.2, and that's roughly, we're trying to match the thickness of the implant in this technique. But I'm changing the rotation now.
So if you look at the top left, Doug is adjusting the rotation of that femur. So you can see it's moving in 1/2 degree increments.
Yep.
So this is really where you start to see the value of robotics, right? You can virtually place an implant with just an incredible amount of precision.
And I can go and I can surface match with this, which for certain techniques is really critical. So like, watch this, and I can go to a CT view, and now I can actually surface match so that, let's look at, this is a side view of the tibia. So I can actually say this blue is a representation of the tibial implant. And so I can line that up so that it's basically matching the surface anatomy. So here's the insert that I'll put on there. Let's see if I can, there we go. So I can actually line this up so that it roughly matches the patient's native anatomy, which gets close to kind of that restoration of kind of that patient's specific anatomy. And this system allows you to do that type of thing because you're looking at their actual anatomy. This is a CT scan of this specimen that we're working on. So it really adds functionality that a lot of the systems out there, really most of the systems out there that are imageless, which are not based on patient's actual 3D imaging, you just can't do this kind of thing. So we haven't touched the patient yet, but this is kind of my initial plan. I think it's a pretty good plan. I'm ready to start talking to Ani if
yeah, go for it. So the next step is registration. So this is where we have the patient CT scan. And if you could see, there's what look like 2 antennas that are coming off the femur and the tibia. So what we have to do is tell the computer how those antennas that our tracking camera can see, how they're oriented with respect to the bone. So we do that via a process called bone registration. So we're going to start with the femur, and we're going to get this checkpoint, and every Monogram system is about safety. So the checkpoint is really kind of a check position to just make sure that everything's where it needs to be throughout the procedure. So we'll start with that.
Okay, Ani, you ready to roll?
Yes, sir.
Now, one thing just before we start going, so Ani, he's done this exposure. So you've got everything tight. You've got 2-pin fixation on each bone, so they're rigidly fixed. You check the tightness. You've got your checkpoints in there in both bones.
Yes, both of them.
And you got retractors set where you want them.
Yes, I have
Basically,
one on the
patellar
left.
tendon. For now, we'll put another one in later.
For those of you who don't know, Ani is not an orthopedic surgeon, but he's almost one at this point.
I mean, he's done more knee replacements than any of my residents have at this point. So, so Ani, let's go ahead and do our femoral checkpoint.
All right, sounds good. So I'm going to have my probe put into the divot on the checkpoint and go. Okay, awesome.
Okay, so I got it here in New York. I clicked and collected that point.
That was pretty
Okay,
interesting.
now we're going to do our initial alignment. This is an augmented reality function. So Ani's lining that up to match the native anatomy of the shaft of the femur and where he thinks the hip is.
Mhm. So as
that gives
far
us-
as we know, we're going to be one of the first companies to really combine augmented reality with surgical robotics to make the workflow more efficient. So it looks like we got a nice initial alignment, and now we're going to start capturing our
Yep.
points.
Okay, Ani, we're ready to go.
Could we clear the last point, Doug?
Do I
Clear,
now?
clear the last 2 points?
Clear the last 2 points?
Yes. Can? Yes.
Okay, you're
Awesome.
clear.
Okay, I'm gonna be ready for registration on my call. Okay.
Okay,
Awesome. Okay. On to the third point. Okay. Go ahead. Okay. Okay. Oh, okay. Okay, on to the tibial femur shaft. Okay. 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 Try that again. Awesome. Okay. Try that again. Awesome.
okay, you're good. You're good, Ani. Great. So you got that in 12 points.
So now we know where that femur is in space because we're tracking that array, and we now know how that array is oriented with respect to the bone. And we know what the bone looks like because we have the CT.
Yep. And that initial step of using augmented reality allows us to collect far fewer points because it gets us roughly in the area, and then the points just help us refine the position. I mean,
Yeah.
in layman's terms.
How much user skill would you say was involved in that?
I mean, not much. It's pretty easy to eyeball that, and like most systems out there collect a minimum of 40 points per bone. You know, you're looking for us like 10 to 12 points, so it's a lot fewer points. It just speeds things up a little bit. So that's great. Ani, let's go on to the tibia.
Okay.
So ready for tibial checkpoint? So I'm kind of advancing to the
Sure.
next screen.
So Cameron, while we're doing this, just a quick point. How did you make the latency what it is? I mean, it's incredibly impressive.
Well, we're using the state-of-the-art technology. We are using the best inter-process communication protocols out there, and we have tweaked it and optimized it to our needs. And that, in addition to the architecture that we put together on our system platform, and also in addition to the way we perform the cuts that you're going to see in a little bit, the combination of all these things allow us to perform resections through a teleoperated system.
Great.
Yeah.
Good.
All right, Ani, let's do it, baby.
Let's go.
Say the word.
Okay, I'm on the tibial checkpoint. Go ahead.
Okay.
So now we're doing exactly what we did on the femur. We're going to do it on the tibia. So
Okay, so tibial alignment,
we're now going to register the position of the tibia.
Okay.
and I'm gonna flip the bone, Ani. Okay, you're good. Tell me when you like it.
Yeah, this looks good to me. Go ahead.
That looks good. I got it.
Oops, sorry. All right.
Oop.
Let's clear that one.
Yep.
I must have moved. Yeah. Okay.
I'm clearing it. Okay,
okay.
ready?
Yes, go ahead. Awesome.
Okay, good.
The tibia is a little more challenging technically to register than the femur, just because the anatomy is a little bit flatter.
Okay, Ani, whenever you're ready.
Okay, on to the
But,
first point. Go ahead.
Our algorithm at this point is really
Okay.
robust on both.
Okay. 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 Let's do that again. Okay.
we do the initial alignment?
Yeah, we could go back to the previous step, clear all points, and then go back to initial alignment. Maybe we redo that step again.
Okay,
Clear that? Yes.
I'm gonna clear it
Okay.
and ready to go whenever you are.
Okay, I'm gonna put in some extra effort to make sure my alignment is good. Okay, try that.
Okay, good.
Okay, on to sample points.
Okay, that was good.
Okay,
Okay, here we go.
capture. Okay. 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 Okay, let's try that again. Capture again, please. Okay.
Doug, let's do the initial alignment one more time. I think you clicked it while it was in the way, up in the area.
Can I have the view
Okay.
of the ankle in here? Because I can't see.
Okay, Ani, go ahead with initial alignment. I'm good.
Okay,
Let me maybe adjust.
sure. Yep, that's better. Okay, that's probably
Much better.
Oh, that's better, guys.
Can you move it more?
Okay, go ahead.
Okay, guys, got it. Okay, tibia.
Okay. First one. Okay. 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 Okay.
I-
Okay. Take that. Okay. Okay. Okay.
9 points.
Okay, we're gonna take some more points on the lateral side, okay? Okay. 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 Okay,
Can you get one on the lateral plateau?
yeah,
Looks like the initial alignment.
go ahead. Okay. Try that. Okay,
Maybe we should fly Doug from New York. Yeah.
Can you do a
alignment was-
posterior medial, Ani?
posterior medial, yes. Okay, try that. Try that. Okay,
Okay, let's clear the points, Doug. Let me adjust the
Yep.
tracker one more time.
Okay. You want to go back to initial alignment?
Sure.
Okay. I'm going to clear that then.
There we go, guys. That's so much better.
Yeah, that's a better shot.
Yeah, it was out. Straight, yeah.
Okay, now we can see it a lot better.
Ani, that looks good, right? That's perfect right there.
okay,
I'm going to click, okay? Don't move. Get that collected.
okay, third time's
Okay,
the
we
charm.
got it. Looks good.
All right,
Yeah.
let's try this again. Okay,
Ready?
yes, capture. 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 Let's go posterior medial, capture. Plateau, capture. Okay. Capture. 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 Excellent. Capture. Okay, capture. Ah, awesome.
Got it.
Yeah. Okay, there we go.
Good job, guys.
So now we know where the femur is, or the tibia, sorry.
Okay. So, should we go to planning, Ani?
Yeah, we can go into intra-op
Whoops.
and recess.
Okay, hold on. Okay, I got it. So what we're looking at here, and Ani can also talk about what he's seeing. This is going to, Ani's going to stress the knee, and we're going to register what the soft tissue tension is, and then adjust our plan to get it where we want it. And every surgeon does it a little differently. So let's go ahead and stress it in extension.
Extension. Excuse me. So I'm going to be applying, so I'm going to put the knee in extension approximately.
So you can
between
see what's
0
happening on the guidance app, right? The bones are moving because we now are tracking them. And we're tracking them with a pretty accurately. So
Okay, Ani, so what do you have now?
So I have the knee in extension. So we need to be within like 0 to 10 degrees of extension. And what I'm going to do right now is going to apply a valgus stress, which would mean the medial laxity is something that you want to capture. So on my go, maybe you can go ahead and capture. So I'm applying valgus stress to the knee.
All right, so you've got 26 millimeters.
Yes.
I'm capturing that.
Okay.
Okay, and then lateral,
Okay. I'm going to apply valgus stress here.
27. So that's good. I like about a millimeter looser on the lateral or outside of the knee than the inside. That's too big of a gap, so we'll fix that in a second. Well, let's go to flexion and see where we are there.
Okay.
So, Ani, you're going to do flexion a little differently than you did extension, right?
Yes, sir. So for flexion, because we can't necessarily apply valgus stresses, what we're going to do is use this device called a cob. It's frequently used in the OR, and what we're going to do is slip in between the medial aspect of the joint, and then I'll have you collect the medial laxity values. So I'm going to make sure first my flexion is in the range that we have set it out. So somewhere between 90 and 110 is where we need to be. So it's at 100, right smack in between. I'm going to gently insert the cob elevator. This is to make sure we capture the laxity of the soft tissue on the medial side. So I am ready here. Go ahead, capture.
Okay, so 25 is your max there?
Yes.
Okay.
26.
Oh,
Yes.
20, you got 26.
Yes.
Okay, I got it. All right, let's do the lateral side. That looks nice. So 26 matches our extension.
Okay, I'm on the lateral side.
31, 32.
Okay.
So that's 31.
So I want it to be a little looser on the a couple millimeters, 2-3 millimeters looser laterally in flexion.
Sure.
So we're a little looser. So I'm going to tweak this now. First thing is our tibia needs to be resection is just too much. So I'm going to go ahead and take a couple millimeters out of the tibia, and let's see what that does. And I'm going to give you a little bit more Barris. Now let's see what that does to our numbers there, Ani. So I took a couple millimeters out. Go ahead and re-stress this in flexion.
Flexion. Okay. So I am back to the medial. Hold on. Okay. Take that.
Okay, so you're 23 now?
Yes.
Okay, I'm collecting that. And how about lateral?
So lateral, go ahead.
So still a little bit much. Okay. I'm going to give you, what do you got there, 23?
Oh, sorry, I took it out. Yes, you had it at 29 or 27. Yeah. Go ahead, capture that.
Okay.
That's the lateral gap. Okay.
Now let's check medial.
So Doug, what are you capturing right now?
So I'm capturing the outside part of the knee, the space between the bones, which is basically represents the tension on the soft tissue.
Mm-hmm.
And that's kind of what makes that's what makes a total knee feel good versus not good, is how well you kind of
How would you do this if you didn't have a robot?
I mean, you eyeball it, which we always think we're better than we are at. It's not very precise. We have various spacers that we kind of stick in the knee and wiggle around to see if they're essentially symmetric. But to fine tune it at this level is pretty much impossible to do just with the crude manual instruments. It's very hard to do. So this allows us to really go from just symmetric rectangular gaps like we've always been doing it to really restoring patient anatomy, which is more like a couple millimeters looser here than there, a millimeter looser here than there. And those little differences really make the difference between whether a patient feels like it's a natural, normal knee versus feeling mechanical and just not loving it. So, okay, so where are we on? So your lateral side?
So I'm back on the medial side in a second.
Okay, so you're 24, 25.
Yeah. Go ahead.
25. So I'm going to capture it. Oops, sorry. Okay, I got 25. Let's go back to the lateral side.
Okay. Okay.
So it's a little bit more than what I want. I'm going to tweak it just a bit. I'm also going to take a little bit of slope out of it because I think we're just a little too loose. Inflection. So I'm going to go to like 4 slope. Okay, let's see that. Ani, are you on lateral side?
I'm still on the lateral side, yes.
Okay. Okay, why don't you release your top for a second? And, oh, so 22. All right, so let's try it with 0 slope. Go ahead and give that a shot.
Okay, put that back in the lateral.
Yep.
Okay.
All right, great. And you can also start tweaking the femur. Like, for example, let's say, and I wouldn't normally do this, but let's just say I wanted to see it's changing that number now. So now we're 25 and 23. That's pretty good. Let's let me go back. Let's check our our medial side one more time.
Okay. Okay, medial.
25.
Mm-hmm.
Let me collect that. Okay, and lateral one last time.
Okay.
25. I really want it more like 27. Give that one more shot laterally.
Did you want to internally? Yeah, that's good.
Try that.
Yes. I know.
26.
Yes.
How about now?
There it is.
27. Okay, good. So I'm going to let's go back to extension, Ani, one more time.
Sure.
So this is really, the point of robotics is to let surgeons do what they're trained to do and make these types of tweaks and really focus on putting the cuts exactly where they need to be versus kind of eyeballing them, as Doug was saying.
Yep. Let me just change this a bit.
Okay, Doug. So I'm applying valgus stress, and you can collect the medial.
Okay, so I'm going to extension and medial. You've got 25.
Mm-hmm.
Like it. And let's do lateral. Are you doing lateral right now?
Oh, yeah, one sec.
Okay, 26. Perfect. Perfect. We love it.
Okay, awesome.
Hey, Doug and Ben.
Okay, that's great. So I'm going to go ahead and take a little bit more off a little less off the tibia here, because our gaps are just a touch big, and that is real good. Stress that one more time, Ani.
Extension.
Just 19, 20, 21, perfect, and lateral.
So this is medial gap,
Yep. And that, okay. Let
and then
me
the
get
lateral
that.
gap lateral gap is 20,
Oh.
25. Okay.
What are you doing, lateral?
Yes, opening up the
Okay,
lateral.
got it. And let's do medial.
Okay.
Got it. Okay, that's
Hey,
pretty
Doug,
good.
Doug and Ben, there's a question from the chat going on right now. Is there a technique or device which integrates with this system that will allow the measurement of the force being applied during the varus valgus stressing throughout the range of motion?
You want to talk about our tension, Ronnie?
Yes. So
So Smith and Nephew has a very slick tensioner that allows surgeons to do that. Our tensioner's simpler, but really does the job. So, yeah.
So this is calibrated to kind of the tension that a normal knee would be under, which is like between 100 and 150 newtons. So
Yeah.
that's basically it. And so we can use that to calibrate our tension and get it exactly right. We're still kind of working on some design optimization so you can fit it in there.
But something that's really important, I think, Doug, is like having the CT scan allows for a more accurate registration, and it's a patient-specific plan. So these gaps mean more, I think.
Totally.
It also allows you to resurface. So a lot of technologies outside of Stryker are tibial first. So you're resecting the tibia. It's just a different type of surgery. We think that, I think Stryker calls it functional alignment. Is that right, Doug?
It's functional, anatomic, kinematic.
But, you know, emergent literature really suggests that they're onto something with that. And you really do need a CT scan to personalize robotic surgery.
Certainly helps a lot.
Helps a lot.
To really
So-
dial it in. So
Yeah.
you're tensioning the medial side now?
inflection.
One of the
Ani?
challenges of
Okay.
a lot of tensioners is they rely on making a tibial cut first, which we don't think is ideal.
So we're at 20 there. Why don't we check lateral? Just to see.
We've talked about for our tensioner, if you do your femur cuts first, tensioning it after the femur's been cut.
Yeah, that thing's hard to squeeze in there. We're
Yeah.
still working out the design tweaks there. 23, that's great.
Yeah. So right now, what Ani's doing is he's using our device to tension the knee to exactly 150 newtons, which is what the literature suggests is the right tension. There's a lot of surgeon variability in how they stress the knee, so we want to take all of that out of this.
And just since we're playing with the tensioner, Ani, you want to use it in extension?
Sure.
Just to make it kind of uniform? Ani's the hardest working man in orthopedics.
So this is why having a navigated robot is so important. You'll see us saying our robot is navigated, our robot is navigated. That just means we're tracking the femur and the tibia, and it allows us to do these types of assessments, which are critical for a patient to feel better.
Okay.
Okay, Ani. So you're
I'm in the
medial or lateral?
Lateral right now.
Perfect. So you were like 22, 23. That's good. How about medial?
It's not actually as trivial as you would think to find these gaps. So these laxity gaps that you see right now, it's 17 on the screen and 22. How you actually measure those gaps is actually a little more challenging than might immediately meet the eye. You're basically trying to measure the distance of a curved surface to a flat surface, and it's not immediately intuitive where you should be measuring from. So some of these things have taken us quite a bit of effort to refine.
Okay. In the
Your
track.
Okay.
I don't think they're tensioning yet.
Okay, so I have the tensioner in the medial aspect.
Okay.
Oh, yeah, there you go.
There you go.
There we
There you go. Okay. Medial.
Yes.
Okay, so you're like 20. That's perfect. So you're a little tighter inflection and extension than flexion. I think that's a pretty good plan, guys. So let's do it.
Sure. So now Doug is going to drive the robot with the foot pedal and make all of the bone cuts.
All right, so I'm going to get the knee positioned to allow all the cuts to be made safely. So he's going to put the knee in a bent or flexed position and lock it down in our holder.
One advantage of our system is we have 7 joints, so we really have minimal robot and patient repositioning. There's no tool change. You make all 6 cuts in one go, and you really don't have to do much in terms of touching the patient during cutting.
Hey, Ben and Doug, more questions from the chat. People want to know how our system compares to competitive products. Also, what is tracking accuracy, and how is the operative time compared to the competitive products?
Sure. So when it comes to competitive products, I think that's a big part of why we're doing this live stream. We're about to do surgery 2,000 miles away from the patient, right? As far as we're aware, there's no product on the market that's done a demo like this. I think this is the first time in history it's ever been done. The benefits are tremendous, right? If you just think about where the orthopedic market is going, future clinical applications, really this is what robots should be in the future. They should be tools that allow surgeons to plan, but the execution should be very, very, very straightforward. And that's really what we're trying to demonstrate today, is how we set ourselves apart from the current state of the art, which we're not aware of any system that could do this today outside of the Monogram system with the efficiency that we're going to do it. When it comes to the tracking accuracy, Cameron, can you speak to that?
Yeah.
Yep. So our accuracy is, we have it got to the maximum accuracy you can get with a serial robot, with a robotic arm, basically. Our end-to-end accuracy is below 0.5 millimeter. That's considering the data collection system all the way to the robot accuracy and so on and so forth.
So end-to-end accuracy, 0.5 millimeter?
Yeah, it's around 0.5 millimeter.
So Doug, I've done the safety checks. I made sure everything is rigid and ready to go.
Okay. And
Great.
you got a blade on there?
Oh, not yet. Okay, I'm gonna go ahead.
I couldn't tell if I couldn't see it from all the way over here, but
Ani, why don't you show off the blade real quick? I mean,
All
just
right.
in terms of not being able to plug this in the wall and do surgery, I mean, pretty much everything in our system is homegrown outside of the robot arm itself, the carts, the end effectors, all of the controls. And look at even the interface to the end effector. So it has a pretty audible snap. When it's seated, one hand insertion. So let's get that in there. Hopefully it snaps loudly for the camera.
and that whole saw and motor can be easy snapped out, and a rotary tool or like a Dremel type tool can be snapped in just a few seconds for different types of cuts that you might want to make.
Yeah, so quick release to the robot arm.
Okay, all good, Ani? Okay, so I'm in cutting mode here, and I'm going to enable the robot.
So you're going to start with your anterior cut, is that right, Doug?
Yep, we're going to start with the anterior cut.
Okay.
I'm going to select all the cuts.
So what you're going to see up here on the screen are what look like top-down view of train tracks. So Doug is going to drive the robot along those train tracks. The surgeon sees where the robot's going at all time. There's no surprises. There's no mystery about where the robot's going to go. It's just very, very safe and predictable.
So I'm going to click on Enable Cutting to make the robot go live. And okay, we're ready for the checkpoint, femoral checkpoint.
So this is where we're going to have a sense of how accurate the registration was.
Okay.
What's our record, guys?
Good.
I don't know what our lowest one ever has been, but I think it's...
Okay, go
Are you
ahead,
in there?
verify. Verify checkpoint.
Hold on. I'm going to go back. Let's do it again.
Sure.
Doug, click on femur.
Click on the
Yeah.
femur button, Doug.
Hold on, I'm going to... Okay, there we go.
Go ahead, verify that.
All right, Ani, you on there?
Yes.
Okay.
Doug, you can.
Have it in the right spot there?
Yeah, let's
Try one more
try
time.
that again, please. Yes.
Good?
So this is a check to make sure that the arrays, the rigid arrays, haven't moved relative to the bone.
Okay, please verify, Doug.
Yep.
Okay. In this case, I would say let's re-register. It's pretty quick. Let's go back to femur registration and register femur.
Okay.
So what would have happened here is, so this is a check to see, you know, if the surgeon knocked the array, basically, or nudged it.
I'm going here.
Okay.
And so if it's outside of an acceptable limit, we would re-register.
Okay.
So
Okay, on. Ready?
Yes.
sometimes one of the challenges of cadavers is sometimes the bone quality isn't great, and it's hard to get those
Okay, initial alignment.
arrays locked in there.
Okay. Go ahead.
All right, I'm flipping the bone. Oh, sorry.
Flip the bone, please. Okay, collect.
Okay, on say the word.
Yeah, there it is.
Yes,
You
go
good?
ahead. Yes. Okay, sample points.
Okay, we're good. Okay, sample points.
Second.
Hold on, I'm gonna deselect that one.
Okay.
Okay.
All right, go ahead. First one. Next. 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 Go ahead. Okay. 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 Awesome.
You're good.
What?
All right, so I'm gonna go back to cutting.
We get a lot of questions about, you know, how safe is it with robotics? That was just a perfect example of safety, right? The system detected that the array had moved, and so we.
Say the word, Ani.
Okay, go ahead. Awesome.
Perfect.
Okay.
Got
Ben
it.
and Doug, quick question. We have a question in the chat, especially now that we had to go back and re-register the femur. What is our ideal surgery time, and how does that compare? And what do we want to say about surgical time?
Sure. So when you look at robotic surgery time, there's a couple of steps that are basically every system on the market today does. That was what you saw was registration, and you saw that we can do it in 12 points plus one initial alignment capture. We have done both femur and tibia in under 40 seconds. I mean, we're doing it remotely, which introduces a lot of complexity. But I think it shows how robust the registration algorithm is, that we can do it remotely, clicking a foot pedal remotely, a surgeon doing it remotely. And then there's the bone cutting, which we're going to get into. I think it's better to talk about that, Daniel, after we've cut the bone, and
Let's do it.
it's more intuitive then.
Ready to go. The robot is enabled, and I'm gonna start going here. So you can see, so that's real time.
So you can see the foot pedal there. So the surgeon can see on the right portion there of the guidance application, basically real time where the foot pedal is depressed. It's a variable speed.
So I'm at about 50% right now.
So you can see there's a cut path labeled 1. So that's going to be the first path that the robot goes on. We call them robot rails, and the robot moves back and forth along these robot rails. So Doug's going to come in at about 50%.
Looks like it's cutting okay from here. Ani, you looking good?
So
And I can see this is kind of like a GPS. It's very similar, so it's intuitive. Like I can see the routes that the saw is going to take.
Yep.
I can see the current route that it's on. I can see where the blade is.
yeah.
The
So now it's
virtual
a number
blade.
2.
And now it's at number 2.
It's going to clean up that little bit of bone there.
And I can see where the next cut is going to be. So I can see cut number 3.
Look at the blade edge
going.
too. So the blade edge is always inside of that bone boundary. We really are very, very conservative about hitting anything.
And I can, since I know where the bone is going to be, I can say, okay, well, I'm worried about some soft tissue in a few seconds. I can move the retractors around
Exactly.
in anticipation of where the blade is going to be going.
So you have both hands free.
Yeah, if I was in the actual operation. That's the.
So
Okay,
femur
so I'm going to pause for a
cut
quick
looks good.
second.
Guys, how does it look?
This looks good, almost like as it was planned.
Okay.
Almost like
Almost like it was planned.
Yeah.
It was planned. We spent a bit of time on that.
Okay, Ani, Ani's clearing a little bone chip out of there that we just cut,
Mm-hmm.
and I'm going to keep going. Okay. All right.
Sure.
So I'm depressing the foot pedal again. I'm a
So we're
little
gonna
bit
do the
of a left
anterior
foot,
chamfer
so I'm
cut.
trying not to do that, but so here it goes.
So we are the first, as far as we're aware, active sagittal cutting robot, and this is very novel. The only other sagittal cutting robot is the Mako robot, which has about 90% utilization on the market today.
Okay, so here we go over to cut number 2, and I've got pedal on the metal until it hits bone, and I'm going to back off a little bit as it hits the bone, just to make sure it engages. Sometimes when a saw hits a round surface, it needs a little bit more time to get through it, but that looks great.
So there's a lot of sclerotic bone a lot of times there.
Yeah.
So we, as a safety, always do 2 passes,
This is kind of a little cleanup cut.
just to clean up.
That looks amazing. And again, I would say, okay, so cut 4 is coming up. It's going to be a little closer to the patella. Ani, you're happy with the patella? It's safe, out of the way? So if I was actually in the operating room, I would just eyeball it, okay, make sure my
Take your time if
retractor's
you
there.
need to. Yep.
And that's it. Okay, so that's our chamfer cut.
Mm-hmm.
Almost like it was cut with a robot.
So let's be careful because he's got his hands in there.
Yep. Ani, I'm going to bring the robot around, okay?
Okay, sounds good.
Okay, here we go.
Here.
Coming around. So this is going to be our distal cut. And again, for that initial cut, I'm going to back off just a bit. Once it starts hitting bone, okay, backing off a bit. I'm at 50%. If I like it, it looks like the saw is getting through that, no problem. Now I can back up too. When I watch this, I'm going to go ahead and
So guys,
back.
just a pinch me moment. Doug is controlling a robot 2,000 miles away in real time. He's registered the femur and tibia. He's planned the whole case, and now he's cutting it.
Yep.
And hopefully it's going to be a pretty accurate cut.
So for surgeons that are on, like if I was cutting this with my hand and I started hitting sclerotic bone, I might kind of feather it a little bit. Now
Yep.
watch this. I can do that from 2,000 miles away. A little sclerotic bone, I might kind of go a little bit slower, come back a bit, and forward.
So the idea is if the surgeon, surgeon control of the end effector, if there's not something they don't like, it's immediately responsive.
Yeah.
Yeah.
It's really, it looks like it's cutting very well here, which is nice.
Yep.
And these cut paths are optimized for safety, to stay, as Ben said, within the bone boundaries, away from critical soft tissues. But if we're nervous at all, if we think we're going to be close, we have our hands free. We have the ability to move retractors around as needed.
The
We know where
surgeon's
the saw's
free
going.
to pick the cut order as well. So,
Yep. There's nothing unpredictable about this. Everything is on the screen. It's showing you where the robot's going next. So
yeah. So right now, what's your velocity, Doug?
right now I'm at about 80% or so.
Okay.
And I can go pedal on the metal, but sometimes when it's getting through a lot of bone, I like to
Yeah,
back
this
off
is
a little
a pretty
bit.
deep cut.
Yep. But it looks great there. Perfect. And I'm going to go pedal to the metal until we get to the next one. And these cuts are just so amazing. I mean,
if you were doing this by hand, are these better than you would do by hand in terms of, yeah,
I would say so. I mean, they're machined basically.
yeah.
So, I mean, they're perfectly flat. And you'll see when we put the implant on, hopefully, that the trials are going to fit really nicely. Okay, Ani, you ready? I'm pausing
Yeah,
for a
let's just
second
pause. He's got
for a
his hand
safety
right there.
check. All good? You got all your fingers?
Yeah.
How many? Let me see your fingers, Ani. Okay, 9.
11.
Perfect.
So if we ever were to commercialize a fully remote system, we'd probably need to,
Yeah. We're not doing this tomorrow,
Yeah.
folks. Okay, Ani, here we go for the next cut. So this is posterior chamfer. And looking good. Here we come.
Yeah, so just notice no blade change, no tool change. We can do all the cuts with one tool. There's been no repositioning of the patient or the robot.
This is beautiful. Now we could, in the future, we'll be able to switch between the saw blade and a rotary tool. So if we want to create features in the implant that use kind of organic features that fit into the bone, we can carve out structures into the bone that allow for really solid fixation of an uncemented implant by switching back and forth between the saw and the rotary tool. So that's built into the system. As Ben was saying earlier, it's really built for lots of different applications.
Yeah.
We're starting with knee, but this is built for every part of orthopedics, essentially.
And we should say we think the future is going to be 3D printed patient optimized implants.
Absolutely.
Period. So that's where robotics are going to really start to shine across the board, is when you reimagine what an implant looks like.
And that's why we're called Monogram. The original concept was take a robot, cut the bone in a personalized way for a specific implant that fits just that patient. And that's ultimately where we'd like to go. So that looks great. So that's our posterior chamfer cut.
So
and one more cut. Ani, safety check. You good?
Yeah, I'm just gonna get this bone chip off.
Okay.
before
I'm not
we-
moving it.
So we've named the robot, like Cameron said, it's the Emboss robot. Emboss. It looks cool when you see it. And the implants are Empress implants. So
I'm
gone with-
going to wait for Ani to give me the thumbs
for
up.
people who are
Okay, let's
BMW
do it.
M3,
Let's do
M5
it.
type fans,
Okay,
it
here
looks
we
a
go.
lot like that.
All right, Ben, I'm engaging. We're going for the last cut here.
Okay.
Mhm.
Loving it. You see, Ani knew where the blade was going. He kind of
Doug, you got a lead foot going here.
pulled. Okay, I'm backing off. Don't get nervous. Okay, and here we go.
Just for the folks on the live stream, we can't really hear very well what's happening. So
Yeah, I can't
we're
hear the
relying
saw.
pretty heavily on the guidance application.
Okay, we're going to cut 2 here.
We should say too that our system has pretty sophisticated controls that are monitoring the feed rate. So the system is also responding to what it's sensing out of the bone.
I mean, that's a beauty. That's a nice cut. One last cleanup cut, and we're done with the femur.
I think this is a pinch me moment. I mean, we just did all 6 cuts. They look pretty good from
I mean,
here.
that looks machined. That looks absolutely perfect. Okay, let's go on
So
to the tibia.
we want, let's just for the audience, let's get a close-up view of those cuts, just to give a sense
Okay, if you wanna-
of the machine finish. Yeah, so maybe you can put something on there, Ani, to show how flat that cut is. That distal cut looks like it's basically a marble surface.
Yeah, and this is where we want to say again, the dramatic move in knee replacements is going from cemented, where you don't necessarily have to have a perfect fit. The cement forgives a lot of sins, to
Sure.
press fit, where you have to have a really tight fit so that the bone will kind of grow into the implant, no cement. And this is where robotics is really driving the orthopedics industry away from cement,
So Stryker has 70% of the press fit knee market today
because they have a robot.
because they have a robot
Yep.
that's utilized.
Yeah, and I just actually read, Ben, in the latest report, they are now claiming as of 2021 that half of all their knee replacements are done robotically, which is pretty amazing. I mean, they are definitely leading the pack there. Okay, say the
Ready?
word, Ani.
Okay, we ready for tibia? Well, Ani's showing off the cuts here.
Oh, yeah.
Okay, Ani, get your hand out of there. We don't want to cut it off.
Yeah. Okay. Okay. Ani?
Okay,
he's
so we're
gonna-
going to do a tibial checkpoint. Hopefully we don't have to re-register the tibia, but we might have to.
Let's see. Say the word, Ani.
Okay, go ahead, collect
You good?
that.
Yeah, we're
Yeah,
going
looks
to
like
have
we
to
have to
re-register.
re-register. Okay.
So, again, it's all about safety. If the system's able to detect if something's moved that shouldn't have moved, and if it moves, we just fix it.
Okay, so while we're doing this, Ben and Doug, quick question. So during cutting, is there an emergency stop button or a stop button? And then how often does the blade need to be switched out? And then people are asking, just to be clear, this is not haptic controls, correct?
Right. Yeah. So there's an emergency button. There are two kind of red panic buttons that are e-stops on the foot pedal.
So the pedal is incredibly responsive. Let's start with that. So we think that obviously we haven't done this, so it's all hypothetical, and I want to emphasize this is a prototype. This is not a commercial product yet. But the response is really, really good. I mean, Doug is controlling the robot from Austin. It's near almost, I mean, the latency is almost undetectable. So
Go for it, on.
the system, if Doug wants to back it up, it's, all he has to do is put the foot pedal in the neutral position. It'll back up faster than he could ever move it with his arm.
Awesome.
So I'm homing the robot to get it out of Ani's way.
Okay.
Okay.
So structurally it looks good. I'm gonna go back to the.
Yeah, there's also an e-stop on the cart, Sanath reminded me.
Go ahead.
Okay. Good.
So we're actually here with Sanath as well. Sanath was our first employee. Why don't you go on the camera over there, Sanath? Yeah.
That looks pretty good. You okay with that, Ani?
Yes.
Oh, a little.
There you
Okay,
go.
that looks pretty good. I'm collecting that.
Yeah, that looks good.
Okay, that's good. Okay, here we go.
Okay.
So again, like just to kind of talk while Doug's doing this, Daniel, if a system that was haptic would require the surgeon to be holding the robot arm, right? So with a Monogram system, you can do it 2,000 miles away and do it perfectly, hopefully perfectly. We'll find out in a few minutes.
Keep going. Okay. 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 Okay.
Looking good.
Okay.
This is
Okay.
actually a question for Cameron.
Yeah, we got it.
Okay, we got
All
it.
right, Ani.
How does the robot avoid cutting where it shouldn't?
Well, we have layers of safety on the system. We have the first and most important layer is the bone boundaries. Those are all registered and defined for the robot. Then the next one is another layer which we don't exceed the boundaries of the implant. The other layer is the collision with all the objects around it, and especially with the bone. And the fourth layer is collision with the
Go
robot
ahead, enable
itself.
cutting.
So we have layers of collision and boundary check.
Okay, got it.
Okay, so we're about to do our final cut, which is the tibial cut.
Okay, say the word, on.
Go ahead, sir.
Oh, hold on. I got to get back to
So,
registration.
Doug's gonna, no,
Oh,
you're
sorry,
good.
enable cut. Oh,
We
sorry.
finished with it. Yeah, that's good.
Normally, there would be an operator that's doing this. The surgeon would be where Ani's standing.
All right. Let's select proximal tibia and do the
Okay.
checkpoint.
So I'm going to enable cutting, which should, okay, there we go. Okay, Ani, you good?
Yes.
Nice.
There we
you
go.
Got it.
Oh, 0.5 millimeter.
Beautiful. So I'm going to get rid of that, Ani, and we're ready to go whenever you are.
All
Good?
right. Everything
Here
looks
we go.
good.
This is the most
Good to go.
complex cut of the 6 cuts we have to make.
So if you look at this cut path here, we've designed this to be what we call gated. So we know where there's a safe window.
Before we start cutting, so Cameron, explain, somebody asked about safety. Just show us explain the gates, point it out.
Sure. Yeah, so on the screen, yeah, you probably see.
Doug, could you pause for a minute?
Now it's making it close.
We can
Okay.
record that, yeah.
Should I, you want me to stop?
Sorry, we'll explain later.
Yeah. Let's make the cut. I think people want to. Let's finish the cuts. You know what we can do? Let's explain it while Ani's clearing the bone out.
Okay. But hopefully everybody can hear us, but you're going to see the safety right here, right? So the blade is constrained to the bone boundary. So you'll see here how the blade will never penetrate the bone boundary.
Yeah, it's hugging the boundary if you look at that corner.
Yeah, so on the next cut, everybody will see it.
Yeah, the next cut's actually, oh
Oops.
boy.
Okay. Doug, can we stop the cuts?
Yep.
Is it running into that?
Yeah, so can we home the robot, stop the
Yep.
cuts?
Let's stop the cut, Doug. Press the red button.
The right button. Mm-hmm.
So as the cutting was happening, I just noticed that this component was loose.
Okay. Oh, okay.
So maybe that was the reason the last time as well. So
Oh,
I'm
okay.
gonna make sure that we
Okay,
tighten
so
it up.
everybody just saw the safety of the robot in real time. The robot detected the array's movement and backed out. Is that about right, Cameron?
Yes.
Yes. Yeah.
Ani, why don't you show what just happened?
So this is the femur array, which is connected via a ball joint to the stem that connects directly to the bone. So this component being loose, this is not favorable. So during surgery, if these trackers move, our system is able to detect bone motion. And because it detects that, it kind of backs out and says, hey, I can't perform the cut anymore.
So that was basically very quick. I mean, that was faster than a human being could have done it. All right, what do we think?
Yeah, it's
Yeah, for sure.
it's around 10 millisecond maximum of response time.
Just that was unintended. We weren't trying to show that feature off.
So we'll have to re-register the tibia, but that's okay. I'm gonna get us ready to do that.
So back to your question around the cut paths. If you go back to the cut file to the bone prep.
Let's register. Let's talk about that while he's clearing out the chips, Cameron, just to keep people engaged.
And Ani, are you sure that the pin is not open?
That is good.
All right.
This is pretty rigid. This component was not.
So we have more questions online.
No, should be good.
Are the implants 3D printed on site? Can you explain press fits versus cement and the cost differences?
Sure. So starting with 3D printing, we're gonna work with ISO 13485 manufacturers for building our implants. And then Doug, why don't you talk about press fit versus cemented? What does that mean, and how many knees are press fit and versus cemented today, and where's that going?
So really simply, cementing, which is the way we've done most knees historically, and the way still most knees are done other than Stryker, it's basically like grouting in a bathroom tile. So you put in a glue essentially that's in kind of a semi-solid form.
Let's start registering just so we can,
Yeah.
I'll carry that, pick up
Okay,
that.
go ahead.
So basically it's,
Checkpoint.
relying on biologic fixation versus bone cement. And this is why the procedure is really moving on from being, a procedure for folks who are 65, 70 years old to even younger active patients are candidates for knee replacements today, because we can use press fit biologic implants where the bone's kind of remodeling over time.
Okay. Okay.
Any other questions from the audience, Daniel?
Okay.
Yes. So we have a couple more questions. I'm going to generalize the stocks question into one simple question.
Okay.
Last time it was $10 per share. This time it's $7 per share. Why?
Okay.
Sure. So the company, we split the stocks. So we're planning to list on Nasdaq. We have a planned listing on Nasdaq with the close of this offering. The next day, we're planning to list on Nasdaq. The ticker is MGRM. And once we list, we'll be trading on Nasdaq. We're working with an investment bank that's recommended the minimum price on Nasdaq is $5, and they recommended that we be as close to $5 as possible. So we did what's called a 1-for-2 share split. So everybody who previously had 1 share, now they have 2 shares, and the price gets cut in half, but you have 2 times the shares. So it's effectively mathematically, it's really no different. But there is literature that seems to suggest that there's more trading volume with lower share prices, which liquidity is we think favorable for our investors, and maybe we can show where folks can buy shares if they're interested. So if you want to buy shares in Monogram, all you have to do is go to invest.monogramorthopedics.com or go to our website, and it's really easy. This is the final investment opportunity before we're planning to take the company public. So this is really the last investment before Monogram is publicly traded on Nasdaq. What we're doing here is pretty complicated. It's going to take a lot of capital, and so our hope is to really access institutional capital as we move the company forward. Crowdfunding has been incredible for us. We're incredibly grateful to our community, and we hope that this gives them an opportunity to have access to their capital. So
Nice. We got it.
We got it. So now we're going to make our tibial cut, and hopefully that array is where it needs to be.
Solid. Listen, this is all spontaneous. This is authentic. This is live. We're tweaking stuff. So like those array holders are not optimized. They're just not. We're improving on these designs. So that's the kind of low hanging fruit that will definitely be improved so that they don't come.
I mean, we're saying that's not the V&V unit. So
And Ben, I want to add that almost everything that the audience see here is the older versions.
yeah, exactly.
Including the
lead
software.
times have been a challenge for us, right? Right, Cameron? I mean, some of the things you're seeing today are not the final product. It's on order.
Cameron, you slowed this down because you knew I was going to be a lead foot, didn't you?
Looks good, Doug. Go ahead.
Okay, here we go. Ani, is that going through the same slot as it did before? Perfect. Perfect. So it's just picking up where we left off. So
we make 2 linear cuts, and then we make a cleanup cut.
Yeah.
And that third cut, you'll see how it really does stay within the bone boundary. So what critical tissues would be over there, Doug?
Yeah, so it's the medial collateral ligament, posteromedially in the tibia that we really want to avoid, because if you cut that in half, the knee becomes unstable, and you can deal with it, but it's definitely not what you want. So that's nice. And this one's going straight across.
So I think it's the 5th cut path that avoids the patellar tendon.
Yes.
So
we'll show that, but this one does too. I mean, because again, we've identified a gate, which Cameron's going to talk about later, where the saw has to enter into that gate every time.
And just to make clear that the cut path is where the blade is actually going to go. It's as intuitive as trains on a track.
Here's the sexy cut here, Ben. This is going right along the anterior border.
Yep.
Now somebody was asking about our competitors. That cut right there that you just saw is very hard to do with the other robots that are on the market. They just don't have the ability to make that.
Does that make you nervous when your residents are cutting?
Every time. It's taken years off my life. I mean, so the but that's it, guys. Here we go. We're finishing that up, and we're done.
Okay.
Beautiful, guys.
So all 6 cuts are done. Now
Doug,
Ani's
could
going
you-
to take it off, and we're going to see whether we hit the target. It'll be obvious from the gaps, won't it? When you
Doug, could
assess
you
the-
home the robot?
100%. Yeah, we'll retrial that and show everybody how that goes. And we're going to go back to
So let's
camera.
home the robot, and
Okay.
then so Doug's going to home the robot.
Okay, so
and
here we
then,
go.
the
Ani,
team's-
watch your head.
Okay.
Here we go. Boom.
Okay. So now's the moment of truth. We'll find out how we did. So I guess Daniel, if there's any questions, fire away.
And also, Cameron, if we don't have an immediate question, you were going to get into
Yeah,
how-
sorry, Cameron.
I don't know what the audience see, but basically, our cuts, maybe on the tibia cut, you saw that the entry port is very small, is just a little bit bigger than the width of the blade. And that's the area that's the area where we can actually safely enter and perform all the cuts. So there's a lot of...
Cameron, can I just interject for 2 seconds?
Sure.
That is, if there are any orthopedists on the call or reps or anybody, we've designed, that's basically akin to the slot that you would have in a kind of a manual instrumentation traditional cutting guide. And that's kind of where we put it. It's a rough, actually even smaller than a traditional cutting guide, but it's very similar to that kind of safety feature that we built into a manual instrument. We've just done it in kind of digital robotic format. Sorry, go ahead, Ken, I'm sorry.
So I
let's,
think you explained it well.
Open the bone, please.
So the most challenging cut probably is the tibia cut. And you saw that we were able to get through a very small port, which we call it a gate. It's a safe gate to enter the bone. And we pretty much stay away from all the sensitive areas on the posterior side of the joint.
And take these
Yeah,
out.
and that's how we're able to execute safe. I don't know if there is any specific questions around the cuts.
Just these two. Careful.
So,
Yeah,
more
let's do it,
questions.
Daniel, if you have more questions.
So people are asking, how many times do we need to switch out the blade during
Zero.
0 times?
So we don't expect to need to switch the blade out. We've heard, anecdotally, we've heard that that's an issue with some other systems. We think we have a really good blade.
I mean, it's definitely, I change the system that I use. I change almost every time. I use 2 blades and sometimes 3, because they just get gummed up with sclerotic bone, because they're thick blades. So they tend to just kind of cake on hard bone, and they stop cutting. Once you see the bone start smoking, it's time to change the blade. So we haven't had that issue with our design as much.
So really what we want to avoid is needing to touch the system. So once it's ready to go, we want people to make all 6 cuts.
Okay. And more questions. Why do we use cadavers? What is the purpose of testing on cadavers?
So you want to tackle that one?
Yeah, I mean, look, we are, safety is paramount here. And we can use cadavers, and we have used cadavers to really refine the cut paths. So all those cuts that you saw where the robot avoided critical soft tissues, all the ligaments and tendons and blood vessels and nerves around the knee were avoided. That is not a trivial task to do when the robot is kind of doing it along these rail paths that we designed. So we use cadavers to iterate and refine the path, the safest path of the cut that the saw can make and the robot can make to accomplish the cuts that we needed to accomplish.
Mm-hmm.
And it really is an iterative process. We learn something new every time we do a cadaver lab. And we've done, what did you say, like 50 or 60?
Yeah.
Something like
and
that.
It's the gold standard for evaluating soft tissue damage. If you've nicked something you shouldn't nick, which obviously happens during development, right? We're trying to figure out what's optimal. and there's no clinical impact of, cutting somebody's patellar tendon, a cadaver, in a cadaver. So
Yeah.
it's really a lot better. It simulates reality very, very well, but there's no impact, right? So,
No, it's extremely valuable, and also just the ergonomics, like how we, Ben was talking about how we've kind of configured things and where how the robot approaches, where the camera is, where the arrays are faced. That was not obvious initially, and we've ended up in a place where none of the other systems on the market have ended up based on the iterations that we've done with multiple cadaver labs. We've ended up in a spot where we think we're maximally efficient, really kind of user-friendly and ergonomic for the surgeon and safe for the patient.
Ani, how's that cut looking?
Cut looks flat.
Okay, maybe let's get in there with the camera and just give it a
Ani,
view.
can I take a look at that resected bone when you get it out? I'm just curious to see what it looks like. Because you can actually really tell if you look at the actual bone that you cut out, you can see does that correspond to the resection that I planned on this planning station? Give you an idea of how close you got.
Yeah. And just going back to the fundraise, right? So Monogram, this is again our last chance to invest in Monogram as a private company. After this, we're planning a listing on Nasdaq. Go to monogramorthopedics.com or invest.monogramorthopedics.com to invest. It's very quick and easy. And yeah, you can be a shareholder before we're a public company, or try to become one.
Let's get a close-up of that bone if we could, guys. I just want to see that tibia bone just to see how close we got. That looks like an absolutely perfect cut.
Yeah. And again, I mean, Doug, how does this compare to the current state of the art? You've used almost every system on the market.
Yeah, I mean, so when you use like the number one system on the market, that's kind of the Gorilla, it's very robust. It's a very nice system, and I use it every day. But for example, on the tibia, a lot of times you just can't cut all the bone because the robot just cannot safely get there. So often we will, we'll have to finish the cuts and do that manually. But let's go ahead and put our trials in. So Ani's got the tibial trial now. And let's externally rotate a bit, guys, if you can. If I can see the tubercle, that looks good. Maybe can you medialize it a little bit so it's not overhanging so much? Not rotate. The rotation was good. Just kind of translated a touch medial. That's it. Beautiful. Now we're going to we have plan. Can I talk about the navigated implant placement?
Yeah, we filed that.
So this is a step that we're trying to take the human error out of it. The position of this tibia is very important. So, and sometimes you can't see all the bone margins. So we're going to navigate this part of it.
Yeah.
So that you get it exactly where you need it to be.
Yeah. So we have, right now we have 20 patent filings and we have a lot more that need to be filed. So we're already working on the next gen, which we think is
Let's do femur first. Yeah.
going to be very, very cool.
Okay. So we're going to go, you want to put a 10 in there now? Put a 10 spacer?
Yeah, we're gonna put the femur in first.
Okay, Doug and Ben, we have a question. So about finishing the cuts, people are wondering, does that make the cut less accurate?
Actually, safety.
With the saw?
So what happens is a lot of there's tissue that clings, right? It's a balance between how close do you go to the bone boundary and risk hitting critical tissue and just, that's really the compromise, right, Doug?
Yeah, exactly. Yeah, no, it depends on how much bone is left.
I mean, but you guys can see it on camera. These are glass finishes.
Yeah, let's get a close up of the femur particularly.
Yeah, make sure, Daniel, that they get up in there to see from the side view of how it looks. And
can we see that? Because I would love to.
It's over here. Let's make sure the live stream is
I mean, that is sexy as hell, guys. I mean, I'm an orthopedic surgeon.
Get in even closer.
I would be
get down
orgasmic
on the
if I had that.
down on the level of it.
Come down to the level.
Yeah, down on the No,
Yeah, and I
side,
can
other
tell you
view.
with the system that I use right
Guys,
now,
direct
the
the,
robotic system,
direct, yeah, there you go, right there.
that it
Get-
would
zoom
never
in.
make that cut.
Zoom in right there.
There are always going to be some gaps and whatever. That is like machine.
Yeah, let's zoom in.
And then come in on this
Absolutely.
side.
Okay, good. All right, moment of truth, guys. Let's put some plastic in there. So these are trial components, folks. These are standard. This is nothing new or improved about this. These are just standard
How does the knee
trial
feel,
components.
Ani? Feel good?
He's just putting the
Putting it in, I guess.
putting the plastic in.
So people want to know, Doug and Ben, how long is the recovery time for robotic versus manual surgeries? Is there less pain?
It's about the same, honestly. It's I would say the big thing is that you improve the outliers. So
Oh, sit down.
you're not so you're not going to have
Let's go check out the gaps.
yeah.
Actually, give it in.
I'll get to that question in one second. We're just checking out the gaps here. So I'm going to go back to the planning. Okay. And let's put our implants back on. Okay. So let's go to full extension, Ani, if we could.
So now the surgeon's able to assess, are they happy with the outcome?
Okay. That looks pretty straight, Ani. Let's stress it in extension here.
Okay.
Oh, mama.
Yeah, so
I'm
basically,
collecting that.
did it go exactly
That's
where
a
you wanted it?
Yeah, how about lateral? Oh, doctor. Love it. Okay, let's go to extension.
It
I'm
is
sorry,
an
flexion. So again, the way we planned this was to be just a shade looser on the lateral side than on the medial side, which is not how we've done knees, just because it's been hard to do that. But that's the way the human knee is built.
Mhm.
We're a little looser on the outside than the inside. We're a little looser in flexion than extension. So let's see.
Did you check the flexion gaps?
You going to flexion, Ani?
Yes.
Okay. Okay. Let's see how we do. Now we can recut too. It's worth saying. Like, let's say something's off with our plan. We didn't predict quite right. If we don't like this, we can always go back in and recut some bone to get it where we need it to be.
So the knee's pretty tight, so the insert, so they're using trials. These aren't actual implants. If they were to use actual implants, it'd get very expensive for the company.
Okay, lock it.
Okay. Go to like 90 degrees if you could.
Actually, just want to get it to 100. Yeah, that's good. Lock it.
Yeah, you had about 90 there?
Yeah.
Okay. And let's get our copy.
Okay, medial.
So 23. Love it. 24, even better. I'm going to go ahead and collect that.
Oh, sorry. Go ahead.
Okay, 23. Love it.
So does this tell you, Doug, that we basically put it exactly where you planned
Exactly. Let's see what lateral is.
Lateral.
Hopefully we're like 25, 26.
There it is,
Oh,
26.
Oh, mama. Hold on.
it? There it is. So basically, perfect knee 2,000 miles away. Is
I
that
mean, that
the
is
headline
hot,
here?
guys. That is a native knee.
So let's
Like-
get the video camera right over and just show how the knee tracks, so everybody gets a sense of that. Yeah. So. Yep.
Yep, and yeah, as you go through your motion, Ani, varus valgus it.
Yeah.
Any
Yeah, it
any
looks-
there much
it looks
play
just-
as you go varus valgus. We might want to go up a shade. We might want to go up a millimeter or two on our plastic, but
And in full extension, it's all straight.
Yeah, so I feel equal laxity in extension, like even valgus varus, none of
Perfect.
them seem too tight or too loose.
yeah,
And then in the same way in flexion, I'm having similar.
it's beautiful. Now
So-
let's check our patellar tracking, Ani, because that's the last thing. Is that if
Yeah.
you've
I
done
think it's
everything right.
safe to say, guys, I think we need to clap right now.
Go-
We just made history. Yes.
There's
Yes.
a patella tracking all along the femoral component.
That looks pretty good, Ani. How's that patella? Is it staying pretty centered?
Yes.
That's beautiful. And you're
Yeah,
not cheating, right? You, take your finger off of it.
Okay. Yeah, I don't see any medial or lateral movement.
That's pretty good.
Yeah.
Yep.
That looks pretty good, guys. I love it. So that's a need where I would say to the residents, this patient can play basketball on this thing because that's nice and solid, and it's going to feel like a native knee as much as is possible with metal and plastic.
Let's get one more close up of the femur, just show how well it. The cuts are basically perfect. I mean, Cameron, what do you think the accuracy of these cuts was? I mean, are you happy?
I would say end-to-end registration, cutting, everything end-to-end is sub-millimeter. I allocated 0.5 for the robot accuracy and 0.5 for the registration. So altogether, I would say sub-millimeter.
I mean, just to reiterate, guys, this is not easy to do and near impossible to do with manual instruments, but we were able to make it. So again, and our gaps in extension were 22 millimeters medial, 24 lateral. And in flexion, 24 medial and 26 lateral, which is really close to the way a normal knee is. And that's amazing that we can do. That's a brand new tool that we now have to make knees, to take them to the next level as far as what the patients feel, which is what we're talking about.
Yeah.
Exactly. Not what the x-rays look like or whatever, but how do the patients feel with this, and what are the complication rates? So like, how many times are you cutting the medial collateral ligament or things that you don't want to cut? We're decreasing the risk and increasing the number of kind of bullseye, balanced knees. So pretty amazing, guys. I really, we had some hiccups with the registration, but really pretty good.
I would say Doug's happy. This is, guys, I just want to say thank you to the team. As a management team, we expect a lot out of you and put everybody under a lot of pressure, and could not be more proud of what was accomplished today. This was a massive achievement, and it can't be understated. I mean, this is, maybe another company's done this before, but a fully remote simulated surgery that went perfectly well. I mean, we were able to overcome anything that was thrown at us. I could not be prouder of the team. So thank you, everybody. Really, thank you.
Great job,
and thank
everybody.
you to the investors that have gotten us to this point. We are incredibly appreciative. We don't take it lightly. We're trying to do everything we can to make Monogram build technology and focus on what we're trying to do. We kind of have a statement of Monogram. We take what we do. We don't take ourselves too seriously, but we take what we do extremely seriously. And our goal is to push forward the standard of care in orthopedic medicine. And this is how we do it. We're trying to say, hey, no, the way the market is today is not how it's going to be 5 or 10 years from now. The way it's going to be 5 or 10 years from now is going to look completely different. And it's going to take companies trying to do risky things, pushing the boundaries, trying to innovate to make that happen. So what you saw today is a fully remote surgery done by a highly trained surgeon with no issues executing a perfect knee.
There's no other system.
I don't know how else we can demonstrate how robust the system is, how differentiated it is. We get a lot of questions, how are you different than the state of the art? The state of the art can't do this, period. We are, maybe they can, and we, haven't done it live streamed, but yeah.
Look at this on here. He barely could get the trial implant off of that femur because it is so tight on.
So
it's amazing.
Yeah, this is really a huge achievement. I'm really proud of the team. Cameron, thank you so much for your efforts and the team for their efforts.
Cameron probably needs a nap, I'm sure.
Actually, Cameron has a vacation coming up. We won't dox you where you're going, but yeah, so Cameron's got some well-earned time off.
Although he might be going to Las Vegas to meet me and Ben at about midnight tonight. You
Yeah.
coming to Vegas?
Undecided. He's gonna figure it out soon.
The Orthopedic Academy meetings
Yeah,
out there.
I just don't want to get all of the credit at all. The team who is sitting here and we're sitting on their desks, they were the ones who put this system
Yeah,
together.
exactly. So we now have 26 full-time employees. So yeah, Cameron, thank you. Yeah, everybody, we're incredibly proud of this team. So
And Ani, fantastic job with the surgery and the back and forth and the re-registering, and amazing job. So
yeah.
thanks.
So again, if you want to be a part of Monogram, you can be. Let me say, we're not the traditional like Silicon Valley funded startup. We're crowdfunded. We're proud of our roots. We're proud that we're crowdfunded. We embrace it. We're not ashamed to be. We're proud of our investors, and there's only one more chance as a private company to invest in Monogram. Just go to our website if you want to support us. If you like what our company is about, what we're trying to do, it's really easy. So, any questions there, Daniel, that we need to address?
Yeah, a couple questions. So why is teleop so important?
So let's maybe have like 3 questions and 3 more questions. Does that sound good, Doug? Yeah. So why is teleop important? So really, there's a number of things that are demonstrated today. Like one is just Monogram clearly demonstrated today what's different about our system. Period. Is there any other system on the market that could do this?
So if you tried to do what we just did with a surgeon kind of watching, but whoever's maybe not trained in the operating room, running the robot and driving the robot with the leading haptic system, you'd get into trouble.
Yeah.
You would cut.
You
stuff
could cut
that you
patella
don't want.
tendon.
Yeah. You'd get into potential trouble. We're trying to demonstrate the robustness of the safety here, that you
Yes.
don't even need a surgeon driving the robot in the same room.
We're not going to talk about all the applications we envision for the future. We have many applications we're thinking about. But this also, just folks watching, get creative. What could you do with a system that was this robust, capable of doing surgery in this way, right? Think about how that compares to the current state of the art, where the market's going. What does the robot of the future need to be capable of doing, and did we demonstrate it today? I think that's the question people should ask themselves. It's not as much about teleop surgery, although we will say that one of the most successful medical device robots in the world, the Da Vinci robot, originally was intended to be a teleop robot. Look where they are today, and just think about what the value add is of a system this robust.
Yeah. I mean, in the
Yeah.
future, we talked about this. There are going to be a lot more joint replacements that need to get done than there are trained joint replacement surgeons. So,
And it's not even joints, right? It's
right.
just
That's right.
we don't want to talk about where we're going next, but the clinical opportunities of a system this robust are significant.
Yeah.
That's all we'll say. Anything else? And we're part of it is right. We don't want to get into IP areas. We're still a startup, and there's a lot of people on this call. So let's move to the next one, Daniel.
Yeah, so one more, well, there's 2 more. The first one's easy. Do you have any plans for other joints?
Well, we just answered that. Let's not count that one.
How long until we get into hospitals? What are the hurdles and the important steps?
That's
from
a
here?
that's a really great question. That is going to be completely determined by 2 things. One is the FDA. So this is a 510K clinical pathway. The big question is whether or not the FDA is going to require a clinical data with our submission. That question has not yet been answered. We've had our initial pre-submission meeting with the FDA. It was very constructive. We got a lot of very valuable feedback. We're making some system tweaks and taking their feedback really seriously. I mean, one of the questions that came up was what happens if the surgeon doesn't have the foot pedal right next to the patient? I hope we've addressed that today, but those are the types of things we have to overcome. So that's going to be something that we're going to continue working with the FDA, and if they need clinical data with our submission, we have a plan and path for that. If not, we have, that would certainly impact our time to market. And then the next thing is just, how the fundraisers go. So if you like what we're doing and want to support us, we appreciate it. Your capital makes a huge difference, right? We have 26 employees. We should have 40 employees right now. And, we have to run our business as conservative as we can, but the more capital we have, the faster we can do things, right? So those are the two variables that will impact our time to market. What we've said publicly is that if the FDA doesn't ask for clinical data, we'll be in the market, we anticipate, in 2024. That's what we've said. We're about to get into what's called verification and validation, and we have a pretty aggressive plan for that. But what happens with the FDA is a little bit, out of our hands. We've hired the best in the world, so we have a CRO, Washington D.C. based CRO, that's helping us. They actually ran the entirety of the presentation to the FDA. So we're doing all we can to try and be persuasive in our arguments, but ultimately it's a little bit out of our hands. So we'll keep our investors tuned on that as we move forward.
Okay, I think those are all the main questions. Just timing and safety and accuracy. Just one last summary about that.
Almost at 2 hours. Good job.
It's enough.
Yeah.
All right.
So yes, thanks everybody for joining us. Any parting words?
I mean, I'm just relieved. I have, I get nervous for this kind of thing, but it went great. So proud of everybody. Thanks for everybody's hard work.
Thanks everybody
thanks
on
for tuning in.
Austin's side. Thank you for tuning in. We hope you enjoyed yourselves. The next live stream is going to be even crazier.
Oh man.
Have a good one. Thank you.